And as we finish up our study of magnets, we're going to take a look at how magnets and electricity work together. Remember that electricity can make magnetism, and magnetism can make electricity. So here we go for section 20, B and C. Ready to begin? And as you notice, only 6 pages you'll need to copy. So here we go. Now you see the picture of somebody's right hand with the thumb pointing up, and the white arrow pointing up means this is a piece of iron. We have an iron bar right here. We're going to run electricity in this direction as you see the arrow and the person's thumb point. We have what we call the right hand rule. Notice again, the thumb is pointing in the direction the electricity is flowing through that iron core, and you notice the spinning magnetic field going up and around, three-dimensional, both in front and behind and to either side. Remember that magnetic fields are three-dimensional. So here's your right-hand rule. Point your thumb in the direction that the electric current flows through the piece of iron, and the fingers will automatically point in the direction of the magnetic field. So what we have is this constant spinning as the magnetic field flows from the bottom to the top. And remember, with magnets, the magnetic field flows from north to south. So in this example, the north would be on the bottom and the south would be on the top, kind of like that picture of the earth we saw in a recent set of notes. But one more time quickly, right-hand rule. Point your thumb in the direction of the electric current, and the fingers will automatically point in the direction that the magnetic field moves. Right-hand rule. Remember that. Ready? Magnetism from electricity. If we have a good amount of electricity, then we can get a magnetic field from something that is not already magnetic. But remember, the 3 ferromagnetic metals are iron, cobalt, and nickel. So take an iron nail, wrap that nail in copper wire or some conductive wire, hook up to a battery. You just made a small electromagnet. And as long as electricity is running through that wire, then this iron nail will be magnetized. All the little bitty domains will line up in one direction. And then that iron nail would pick up very small pieces of steel or iron, such as paper clips. Now, the electromagnet means there is a piece of iron inside the wire coil, and for its size, that's a pretty good, strong electromagnet. Now, it turns out that the more times we wrap that wire around that nail, the stronger the magnetic field, because we'll have more wraps in the same amount of space, which means more electrical energy, which means stronger magnetic field. And as people discovered this, then people were able to realize, hey, how can we get a very strong magnetic field to pick up really heavy pieces of iron, such as this train car right here, because this car has to be moved in the junkyard. Very large electromagnets with strong electric currents and a lot of conductive wire to make a very powerful magnetic field to be able to lift something this heavy and move that object. When we turn on the switch to get the electricity, we turn on a relay to turn on a magnetic field. So relays are like switches that turn on and off magnetic fields. And there you see an example of a very large electromagnetic field and an electromagnet in the junkyard to pick up very large, and I mean very large and heavy, pieces of iron. Ready? So we can get magnetism from electricity, and we can get electricity from magnetism. Maybe you have a generator at home. Power goes out, run that generator, you get to plug in a couple of devices and get electricity. So you don't want to waste that because you're going to burn fuel while you run the generator. So you want to be able to make sure you have good emergency things that you need to run on electricity. Well, what happens in a generator? There are magnets inside. Now, I won't be able to do this as fast as what really happens, but consider my stick here as a bar magnet. So I move this bar magnet very fast, a lot faster than you see right there, inside the magnets, inside the generator. And if we move that magnet fast enough, then we're going to push enough electrons through both directions of the circuit that we will get electricity. So there are magnets inside that generator with coiled wires wrapped around them, but of course not quite touching because we want those magnets to be able to move very freely. The magnet oscillates, moves back and forth 60 times in 1 second. Now, no way can I do that, but 60 times in 1 second. A push, in this example to the right, will force electrons through the circuitry one way, and then a push back to the left will force electrons through the circuitry in the opposite direction. So the magnetic forces are pushing those electrons in both directions through the circuit. And at the correct speed, 60 hertz, we get just the right amount of voltage that will supply the current and the power to run most of our devices that we can plug in. And again, you don't want to waste, because you need to use fuel of some sort, a strong battery or gasoline, in order to run the generator. Ready? Now, how can we use electromagnets? Well, we just talked about a generator, magnets moving very fast, 60 times a second, inside coiled wires in order to push electrons in both directions. We talked about the junkyard electromagnets to pick up extremely heavy, large pieces of iron, such as cars, or in the picture you saw, a train car. Think of monorails at Disney parks and other theme parks to get quickly from one area to another area, maybe all the way across the park. Get on the monorail. Electromagnets propel the monorail across the railing at pretty good speeds and use very, very, very little fuel. Metal sorters. You'd probably have to read the pages 478 and 479 for better descriptions, but push the iron aside by using magnets and allow the aluminum to pass by. So if you have a mixture of iron and other metals, the magnets can affect the iron and not the other metals, and those metals will be able to go through. Think of the safety gate. We don't want little kids or even adults, we don't want them going through the gates when they're not supposed to. Electromagnets hold those gates closed, and then when it's time to open to let people in and out, the operator just pushes a button that stops the electricity, therefore breaking the magnetic field, and we can open and close the gate. So safety gates, and many other things besides this list up here too. Maybe you've had an MRI if you've had a serious injury. I've had MRIs done. Magnetic resonance imaging. These are machines that use electromagnets and other things as well to see inside the body to diagnose the problems. Electric guitars use electromagnets to help amplify the vibrating string. So the string produces a note. Electromagnets will be able to make that note come out of the speaker a whole lot more powerfully, and then your audience will be able to hear you play the guitar. And these are just a few very useful purposes for electromagnets. Ready? We talked about generators, moving magnets back and forth to force electrons into motion. Well, let's look at a motor now. Think of the washing machine. Maybe you've opened up the washing machine and you've seen that tub with the clothes inside spin around and around and around very fast. Well, that allows water to go through those clothes, and that soapy water will help clean the dirt out of the clothes. But what causes that tub to spin around? Well, obviously we have to have the machine plugged in and turned on. The electricity goes through electromagnets, which are lined up with like poles of permanent magnets on that round tub, and a very strong repulsive force spins that tub, and that process continues over and over and over again until the machine stops and there's no more electricity going through. Now think of the pencil sharpener in the classroom. We put the pencil in, we push enough, we get electric current flowing through the motor, and that motor will spin the same way by repelling like poles of permanent magnets, and then the blades attached will sharpen the pencil. We'll talk a little more about transformers on the next page, but transformers take electricity to make a magnetic field to help make more electricity. That's a step up transformer, but then we have to reduce the electricity before letting that energy go into a building, because we don't want the building to burn down, by doing the exact opposite process that you're about to see. So transformers change the amount of voltage, which means different magnetic field, which then means a new amount of voltage leaving and entering buildings. And now let's take a look at the transformer. Ready? All right, let's look at this very simplified example right here. And we see 110 to 120 volts going into a primary coil. Again, it's a whole lot more complicated than this. A very simplified example. Notice that we have 5 wraps of conductive wire around a piece of iron, a little iron square. The electricity comes in, causes that iron to become magnetized. So as the current goes to the other side, the magnetic field will strengthen, and then we'll have going through 10 wraps. In this example, we're going to have more electricity, and a stronger magnetic field will push those electrons with twice the force because there are twice the coils. Now, if this had been 3 times the coils, this would be 3 times the force. So instead of 110, that would be 330. But in this example, 110 volts go in, the iron core gets magnetized, and because there are more coils on the output side, the secondary, more voltage gets put out. Those are step-up transformers. Step-up transformers increase the voltage. Well, now look at the bottom picture, step down. This is coming out of the electric companies such as JEA, going through a series of transformers to be sent through all the power lines throughout the city. And then as we go into different buildings, there's a series of step-down transformers that reduce how much voltage. So the primary coil, in this case 10, the iron core becomes magnetized, and the secondary output is 5. Notice the voltage is getting cut in half by the same ratio. 10 and 5 is half of 10. So whatever the coil ratio is, that's going to be your step up or step down ratio also. But again, these are very simplified examples here. Power plants and buildings have to use appropriate step up and step down transformers. Well, step ups are going to send enough electricity through a city. Now, remember, K means kilo. So we're talking 765,000 volts going through all those power lines, down to most commercial buildings needed 220 volts, and residential homes maybe needing 110 to 120 volts, not votes. Therefore, series of step up and step down transformers all throughout the city and then into the buildings. Again, a very simplified example. It's a whole lot more complicated than that for real. Ready? That is all. You learned a little bit more about how electricity and magnetism work together, and this lesson has a very magnetic personality. See you next time.